You're listening to Skeptoid. I'm Kevin Hoover from Skeptoid.com. Tube amplifiers. The 20th century dawned with an innovation that transformed communications and set today's electronics industry in motion: vacuum tubes. Since succeeded by more efficient miniaturized circuits, tubes still enjoy deep loyalty by musicians and the audio enthusiasts who spend to reproduce their music. Is the ardor for this antique appliance misplaced, with appreciation colored by extraneous associations? Or do the drab silicon successors to gleaming vacuum tubes fail to relate the magic in the music? Grab your headphones, settle into your favorite chair, and crank up your hi-fi as we sound out the signal and the noise surrounding tube amplifiers. But first, some science and history. When electronics pioneer and Marconi Company engineer John Ambrose Fleming invented the vacuum tube in 1904, he couldn't have known that his new device, known as a thermionic valve in his native Britain, would one day allow people all over the world to talk to each other, make high-fidelity music fill a living room, or blast power cords across stadium arenas. His two-electrode Fleming valve was a simple diode, an advance over the primitive cat whisker devices that had gone before. Unencumbered by air, electrons leaped from one electrode to another across a gap, but only in one direction. Just one half of an alternating current's waveform could pass through, coming out as rectified or DC, direct current. Fleming, though honored as the father of modern electronics, didn't exploit the vacuum tube's full potential. The new device was transformed a few years later by inventor Lee De Forest. He added a key component which changed the thermionic diode into a triode. De Forest called the new device an audion, and it did much more than just switch current. But how? In its simplest form, a triode vacuum tube is a glass bulb with all the air removed, containing three central components known as electrodes. The negatively charged electrode, called the cathode, is the part that also makes light. When heated, the cathode boils off electron particles via thermionic emission, or the Edison effect. These hot-to-trot electrons are drawn to a positively charged plate, or anode, elsewhere in the tube. But first they must pass through a control grid. This is an electrode whose electrical properties can be controlled by any small input signal, and with considerable nuance and precision. De Forest's real game-changing innovation was to connect a telegraph key to the control grid, sending it low-voltage pulses of varying duration, the dots and dashes that comprise Morse code. These pulses modulate a variable electrostatic field around the control grid. The field acts as a traffic cop for electrons traveling from the cathode to the anode, allowing the small grid voltage to control a large current. In doing so, it transforms the feeble telegraph key input into a souped-up output signal, which can be sent over transmission lines to recipients elsewhere. Better yet, the grid can be modulated, not just by a telegraph key, but by a microphone or recorded music. This earned De Forest fame as the father of radio, a term he bestowed upon himself. In a famous, rather self-ennobling quote, De Forest proclaimed, "Unwittingly then had I discovered an invisible empire of the air, intangible yet solid as granite, whose structure shall persist while man inhabits the planet." The audion was the first successful electronic amplifier, and in ensuing years it was further developed with fresh variations and enhancements, such as multiple control plates. Initial uses included long-distance telephone circuits, radio transmission, and by the 1920s, moving pictures with sound, the talkies. World War II drove further innovation of tube amplifiers for radio and radar, and tube amps would reign supreme for decades.
The output of a microphone must be amplified before it can produce an audible sound through a loudspeaker. A device used to accomplish this is a vacuum tube amplifier, which increases low energy to a higher level in an identical wave form, or as nearly identical as possible.
Improvements in materials science soon lifted the concept to a new level. Though it had been theorized earlier, it was in the late 1940s that Bell Labs was able to fabricate a primitive transistor using germanium. This effort later won the research team the 1956 Nobel Prize in Physics. Transistors operate on the same principle as a triode vacuum tube. Instead of a cathode, anode, and grid, transistors have a collector, emitter, and base. Current flows into the collector, is modulated by the base, the equivalent of the tube's grid, and flows out through the emitter. Transistors offer a lot of advantages over tubes. They use much less power, run cooler, cost less, and are generally more durable and thus versatile. But the main advantage is that transistors can be vanishingly smaller. The first mass-produced transistors were the size of a bean rather than a potato-sized vacuum tube. Soon, mass-produced products using electronic signal switching and amplification, such as the iconic pocket transistor radio, were flying off the assembly lines. But as far as miniaturization, the best was yet to come. While transistors were a great leap, they still required several support components such as resistors and capacitors to form a circuit in which they could function. Enter integrated circuits, or ICs. Texas Instruments scientist Jack Kirby realized that all the supporting components on a circuit were made of basically the same thing, semiconductor material. Why, he wondered, couldn't they be co-located or integrated into a much smaller circuit on the same hunk of stuff? While such a thing had been previously theorized, in 1958 Kirby unveiled the first working model of an IC, an oscillator circuit on a tiny sliver of germanium measuring less than a half-inch across and just 1/16 of an inch thick. This highly engineered hunk of metalloid earned Kirby a Nobel Prize in Physics in the year 2000. The IC's early adopters were the 1960s military and space program, but it wasn't long before consumer electronics started using them in audio applications and later, computers. Today, thanks to photolithography, where circuits are simply printed, ICs integrate millions, even billions of transistors on a single chip. With recent advances in nanotechnology, molecular-scale computing may soon provide functional transistors made of individual molecules that take advantage of quantum effects for switching and amplification. Even the silicon that ICs are made of could give way to newer, faster graphene. All this great progress must mean that vacuum tubes, like buggy whips, wax cylinders, and floppy disks, have wound up in the dustbin of technological history, right? Wrong. Like wristwatches, vinyl records, and even film cameras, there are those who eschew whiz-bang silicon for the comforting, bulky old tech of yesteryear, and that includes vacuum tubes. Tubes enjoy wide use today and show no sign of disappearing. They offer powerful amplification at high frequencies and are used in radio and television transmitters, in microwave ovens, particle accelerators, and other specialized applications. But vacuum tubes' fiercest defenders are those with an ear for music, those who appreciate it, and they who make it. Manufacturers of home stereo equipment have invested heavily in perfect sound reproduction and have all but achieved it. A textbook definition of sonic perfection might be the faithful replication of a signal, in this case music, with no added distortion. The sound coming from the speakers would be as true as possible to the original, a precise, magnified version of the waveform fed into the amplifier. Problem solved! Or not. Take a look at reader discussions on audiophile websites, and you'll find that slavish accuracy in sound reproduction is exactly what many audio aficionados do not want. They tend to favor tube amplifiers, and will pay a pretty penny to get them. Tube amps, they acknowledge, do add their own flavors to the music. Tube fans might describe tube-amplified sound with terms reminiscent of wine reviews, such as round, syrupy, dimensional, swirling, creamy, full-bodied, seductive, or even brown. Solid-state amps might be dismissed as harsh, sterile, cold, or soulless. These highly subjective terms aren't without a footing in fact. In tube amplifiers, distortion, or clipping as it is known, tends to come on gradually as signal amplitude increases and consists of even-order harmonic frequencies. These signal processing artifacts resonate at integer multiples of the original frequency. An even-order harmonic might be 200% of the original signal's frequency, an octave up, and impart reinforcing qualities to the sound. In harsh contrast, distortion in solid-state amplifiers tends to come on abruptly at high power levels and consists of odd-order harmonics which, depending on the specific frequency, can sound harsh and buzzy or have a deadening effect on the music. It all adds up to a complex equation, though diehards in each camp, solid-state or tube, never tire of championing their preferred platform. The debate is a mashup of philosophy, perception, and platform passion. A chip fan might point to stats and graphs that document the similarity of input signal to output signal. It seems logical that this precise sound reproduction better places the source material, the musician, into the listener's presence. But tube trumpeters call that listening with your eyes. Listening is done where music actually dwells, in the mind. Thus, they say, perception trumps data. Hybrid amplifiers try to combine the best of both worlds, but, depending on your sonic philosophy, they may strike you as either a compromise or a synergy. A hybrid amp might include a tube preamplifier to imbue the music with the desired euphony, then send the sweetened signal to a solid-state output stage to pump it up with clean, accurate power. Tube amps are especially prized by today's electric guitar players. Whether they're looking for the lovelorn liquidity of pedal steel or the crunch of metal, guitarists are among the most impassioned tubists. Shredders especially. For them, distortion is an essential tool of the trade, if not a basic human right. Achieving the suitably torrid tone takes the right guitar, effects pedals and outboard equipment, and typically a tube amplifier, sometimes turned up to 11, to fully infuse it with what's been called the positive menace of heavy rock guitar. Multiple major manufacturers service the music industry with ever-evolving lines of tube, solid-state, and hybrid amps. There are scores of A-list household name guitar players in both camps, who will mix and match their gear to create a signature sound. Adding yet another layer of complication and controversy to the situation is the advent of amp modeling. Digital signal processors, or DSP chips, can digitally shape a signal and allow a solid-state amp to emulate tube amplifiers. A musician may choose tone characteristics of individual amplifier brands, generic tone styles such as surf or metal guitar, or eras in which a certain tone was introduced. DSPs can also mimic the characteristic tones imparted by specific guitars, effects pedals, and speaker cabinets, albeit with varying degrees of sound-alike success. YouTube is loaded with A/B comparisons, and they sometimes confound expectations. Still, the basic tube amp soldiers on. Even the fanciest of today's guitar amps, with all their add-ons and digital enhancements, still rely at their heart on the basic thermionic valve. In both guitar and home stereo amps, many factors can affect sonic performance and perception, including other components, their quality and interaction, room and equipment temperature, radio frequency interference, vibration, and limitless unquantifiable factors. Sentiment is one when a type of device or brand holds fond associations with a classic artist or a memorable experience. Coolness can't be discounted either. Tubes carry the cachet and romance of old-time radio and early rock and roll. Their retro, totally tubular look and comforting orange glow present a pleasing visual, one maximized by some manufacturers. To enhance the cosmetics and buyer appeal, amp makers sometimes mount the Jules Verne-like glass tubes in prominent, needlessly exposed locations that make them susceptible to interference and damage. Listening with the eyes, it turns out, goes both ways. If you're agnostic as to platform, a well-made product of either type could be right for you, or maybe you don't care at all. In the end, it's a personal choice as to whether you use a sheet of silicon or a glowing glass tube to attain mastery of the invisible empire of the air. Skeptoid is not just a hobby, it's a non-profit public charity. Just as you depend on a new show every week, we depend on your monthly micropayment. If you're not already a supporter, please come to Skeptoid.com and click on Support Skeptoid and make this a two-way street for many years to come. You're listening to Skeptoid, a listener-supported program. I'm Kevin Hoover from Skeptoid.com.